So two more step two questions here. Questions 1 and 2 from the equations and inequalities support booklet. This one and this one. We'll do this one first up here. You can do this entire question just by being very confident with sketching of graphs and very confident with graph transformations, and everything after that kind of just falls into place. So let's get into it. Let's sketch this graph. There's probably lots of ways to sketch a graph like this, but I thought I'd do it in the laziest possible way, which is just to think about what the graph x to the power 4 looks like, which is obviously this. X minus 1 to the power 4 is just that graph shifted right by 1, and this one shifted left by 1, so you end up with these two graphs. And when you add two graphs together, all you're really doing is taking any x point and just adding the two heights of the graphs at that point. So, for example, when x is 0, you're just taking the height of 1 and adding it to the other height of 1 and getting a height of 2. And so the graph is going to be here in the middle. And when you have when you've got x equals 1, you do 0, because that's the height of the green graph, plus whatever the height is here, and you get to here, of course. Now, the question is, does it kind of go down or just immediately start going up? And it just immediately starts going up because the blue graph is rising at a faster rate than the green graph is falling when you move slightly to the left of the origin to try and add these graphs up. The green graph has increased by more than the blue graph has increased by more than the green graph has fallen. And I can argue that because the gradient of the blue graph must be steeper here because it's further away from its turning point than the green graph is here. So it must just head straight up, and likewise on the other side. And you just end up with a graph that looks a bit like this. GeoGebra does it like this for me, which is just much nicer to work with. So we'll just leave it like that. Anyway, now we have this graph needs to equal some value c. So to deconstruct this, all we're really asking is, when does this graph, the one I just drew, intersect the graph y equals c? Right? Because if we were asking this, we would just set these equal to each other and get this. Well, the graph y equals c is just a horizontal line, right? Like this. And if we just shift that up and change our values of c, we can see that if c is less than 2, there are going to be no solutions, right? If c is bigger than 2, there are going to be two solutions. You can see it passing through twice every single time it goes through here. And if c is equal to exactly 2, then we're just going to be tangent and cross it once, and that gives us all the conditions that we were asked to get. And so we're done with part A. So that's nice and good and done. Part 2, how many real roots does this have? So if this is the graph f of x, this one just up here, then just notice things to do in step all the time. Just, can you find a way of making the question you're being asked to do just the same as the question you just did? And I think there is, because if we just consider the graph f of x minus 2 and just take away 2 from all of the x inputs, we just immediately end up with the graph they're asking us to look at. So therefore, the graph they're asking us to look at is just the graph we were just doing, shifted right 2 places. But of course, if you shift that graph right 2 places, that changes nothing about the C answers that we had before. Still no solutions down here, still one solution when we get there, still 2 solutions up here. So nothing changes from before, and so we still have those same answers there. Next one has some mod functions, which is kind of cool. So we're going to have to go about sketching this. There's a few ways of doing this. If you've taken Temua, then you should be fairly familiar with my kind of method for dealing with these mod functions. I say my method, it's not my method, just the method that I use whenever I see them. I'm just going to think about when the mod is just going to do anything and when it's going to times the whole thing by -1. First thing to maybe say is that when we're sketching this, y is never negative because this is a positive thing by definition, and so is that, and you're adding them together. Now, when the input in the mod is bigger than 0, mod z does nothing. And when it's less than 0, we just think of it as timing the entire input by -1. So basically, when x is bigger than 3, or equal to 3, really, this whole thing is just x minus 3. The mod function is not going to do anything. When x is less than or equal to 3, this whole mod function, or less than 3, I should say, really, this whole mod function is going to become minus x plus 3, because it's going to times the whole thing by -1. And likewise over here, we have a dividing line now, right? So when we're sketching this, if we're over here, this is just going to be x minus 3, and if we're over here, it's going to be minus x plus 3. And likewise for here. So if x is bigger or equal to 1, it's just going to be x minus 1. And if x is less than 1, it's going to be minus x plus 1. So we're going to combine that together. So over here, both values, we're bigger than 3 and we're also bigger than 1, of course. So this graph is just x minus 3 plus x minus 1. That's just all that this graph is, which is 2x minus 4, which is, as a sketch, we can just find a random point, or not a random point. I found the point on the line x equals 3, which is, of course, 6 minus 4 is 2. So that's that point there, and it just has a positive gradient, so it goes up like this. In the middle, this is being times by -1, so it's minus x plus 3. This is still positive, so it's just x minus 1. So we end up with, I've done the side first, I'll do the middle first. So these two things cancel out, and you end up with y equals 2, which is just a flat line here. And then like you can see I've already done this one where they're both negative, so minus x plus 3, minus x plus 1, minus 2x plus 4, goes to this point here, negative gradient like this, and you end up with this sketch here. Now, how do the same thing with the c thing. Like so clearly when c is less than 2, there are no real solutions. When c is bigger than 2, there are 2 real solutions because we're going to get up and cross it twice up here. Now, what happens when c is equal to 2? Is that one solution? Well, not really, because here's a solution, 1, 2. Here's a solution, 3, 2. When x is 1, when x is 3, I should say, maybe. But also when x is 2, or when x is 1.5, or 1.2, or whatever. There are actually an infinite number of solutions along there. So that would be our conditions on that one there. Good. And the very last one, how many row roots does this have? There's not really any way to, I don't think, to transform what we've looked at into this. So I just went back to basics and just sketched this from scratch. Lots of things to do. Assess extreme points, find roots, find the y-intercept, and find the turning points. That's all the things that I'm going to do. So y-intercept happens at x equals 0. We can just plug in x equals 0. We get y is minus 28, so that's easy. When x is massive, we're going to get a massive number cubed plus a massive number cubed. That's clearly a massive number. When x is massive and negative, we're going to get a massive negative cubed, which is massively negative, and another massively negative cubed. So they're going to combine together to make something very negative. So that's that done. That's that done. Roots. So let's set this equal to 0. When y is 0, set that equal to 0. Move this onto the other side, I guess. And now I can cube root both sides. And the reason I'm allowed to do that is a couple of reasons. Firstly, when you cube root a product, you can just cube root the two things separately. And the cube root of minus 1 is just minus 1, because minus 1 times minus 1 times minus 1 is minus 1. And I can also kind of just cancel out the cubes here, I think, just to get essentially, therefore, minus x minus 1 equals x minus 3. And I can do that because cubics are like one-to-one functions, right? Like they don't act like quadratics. There's no case where, you know, if you have x squared equals y squared, you know, that was 5 and minus 5 would satisfy that. If you've got cube roots, or cubes, we should really think of at the start here, then the inside of these cubes must be the same, because positives, cubes, positives, and negative cubes, negatives. There's no ambiguity there. So I think I can just do this. And where am I going with this? Okay, I'm solving this for x, of course. We get x equals 2. So there's a root at x equals 2. So fantastic. Last thing to do will be turning points, or stationary points, maybe I should say. So we're going to differentiate this. I've colored this in just to be really clear about the chain rule that I'm doing here. 3 times the derivative of this is 1, and then this to the power 2, and so on with the other one as well. It all clears up to this. Stationary points happen, obviously, when that equals 0. Divide everything by 3. This is a square thing plus a square thing. So both of these are positive or 0. So to make 0, both of them have to be 0 at the same time. Are they both ever 0 at the same time? Well, of course not, because this one has to be 0 at x equals 3. This one has to be 0 at x equals 1, which is not the same time. So therefore, this is never equal to 0. No stationary points. So while it can curve a little bit, it can't ever go flat or turn. So it must look a bit like this. And therefore, when we do our y equals c thing, which we've done this whole time to find the number of roots, it's just one root all the time, right? Just one root all the time. Nice and easy. And that would be that question done. Question 2 then, using this series, by the way, this is called a Taylor series, and that is a great picture of Taylor. Show that e is bigger than 8/3. So, okay, well, the first thing we'll say is that e is e to the power 1. So they clearly want me to put 1 into this, or substitute 1 into this. If you haven't seen the factorials, it means timesing by every inch down below the number you start with down to 1. So, okay, fine. Put in 1, and yeah. Now, these terms are clearly very small over here. If we were to just get rid of them, we would be making this entire side smaller, because we're getting rid of some positive stuff. And if we make this entire side over here smaller, that makes this the bigger side, so we'd end up with e bigger than something. So if we sneakily decide to cut it exactly here, to get 1/6, 3 times 2 times 1 is 6, as our last term, it just so happens that these terms here add up to 8/3, and we end up with our exact thing that they wanted us to get. The next thing is to show that n factorial is bigger than 2 to the power n. Now, to do this, we're going to need to do a very quick induction proof. So what we'll say, I mean, again, this is what n factorial is. This is what 2 to the power n is, obviously, n times. You've got 2 of those. 2's n times, whatever. So, okay, firstly, I mean, we can't show it for n equals 1 because we're showing it for n bigger than or equal to 4. So our first step is to show that it's true for n equals 4, which we can just evaluate, right? 4 factorial is 24, 2 to the power 4 is 16, so it's true for n equals 4. Excellent. So now we can do the assumption step, which is to assume that it's true for n equals k. So we'll just assume this to be true. And now we'll investigate what happens for n equals k plus 1. So replace these with k plus 1s. Let's start on the left-hand side over here. K plus 1 factorial is k plus 1 times k minus 1 times k minus 2 and so on. In other words, it's k plus 1 times k factorial. And we've already shown by the assumption step that k factorial is bigger than 2 to the k. So if we replace this with 2 to the k, we're going to make the whole thing smaller. So therefore, this is bigger than that times 2 to the k. However, k plus 1 is also bigger than 2, as long as k or n or whatever is bigger than 4. So this is also bigger than 2 times 2 to the k. Which of course is 2 to the k plus 1. So now we have a chain saying that k plus 1 factorial is bigger than 2 to the k plus 1. So we can do the usual spiel here, which I think I didn't write down. I didn't. Okay, do the usual spiel about how that shows that it's true. But anyway, we've done it, so that's good. So that's done there. And hence show this thing here. So we need to be quite sneaky with this. We obviously need to use this idea that we just proved to do this. So where can that come in? Well, firstly, notice it's only true for n bigger than or equal to 4. So we've got these factorials in here, but I'm only going to think about them when we're bigger than 4. So if I replace this 4 factorial with a 2 to the power 4 instead, what happens? Well, I'm going to replace, I'm going to make this number here smaller, right? Which is going to make this whole number bigger. If you divide by a smaller number, the thing becomes bigger. So this is bigger than this thing. So if I replace this with that, I'm going to put something in bigger here, which is going to make this whole side bigger, and therefore this will be the smaller side, which is fantastic, because that's kind of what I want here. And actually, I can not only do that for that term, but I can do it for all of the terms thereafter, because they're all bigger than 4. So fantastic. Now let's put a equals 1 in, or x equals 1 in, I should say. And we get this. Now, we already know this adds up to 8/3 because we did it just a second ago. Now, what about all of this business over here? We can't get rid of anything because then, we'd be making this side bigger, and we can't really do that. We need to keep this inequality here. So what do? Well, this here is just a geometric series, I believe. You can play around with it like this if you want to. It doesn't really matter. But this is just a geometric series. It's got an r of a half, and it's got a starting value of a, and it's infinite, or a is 1, sorry, and it's infinite. So it's just a over 1 minus r, right? If you want to do it as 1 over 1 minus r, you can do, since you've got a 1 here. But it's just a over 1 minus r, which is going to be 1 over 1 minus a half, because the factor is a half every time. 1 time over 1 minus a half is 1 over a half, which is 2. So all of this is going to add up to 2. And the 16th times it on the outside, we get this. And let's just add these things together. And what you know, it gives you the thing that they wanted you to get. So that's great. We are done with that as well. So now we can actually bound E nicely, bigger than this, less than this. And of course, if we convert the other one, we'll end up with this here, which is really cool. So now I've got E bounded between those two values. Excellent. Now we're going to ask, it looks completely different, right? We're going to be sketching this curve all of a sudden. So, okay, well, firstly, well, we're not sketching it yet. We're sketching it at the end. Firstly, we're showing it has a minimum point between this and this. Now, usual way to test a minimum point is dy by dx equals 0, whilst d2y by dx squared is greater than 0. Now, that's how you could do it. I'm actually not going to end up doing this. I'm going to have to think of another way, but that would be a usual thing. But let's start with dy by dx first. So obviously, to differentiate this, the 2 comes down here, makes 6 e to the 2x, because this doesn't change. And then log differentiates to this thing on the denominator and the derivative of this thing on the top, which is just minus 1. So it becomes this. We can tidy that up, I guess, a little bit, putting this in there. And then maybe I'll combine these two things here because it still looks very messy. And then 3 can go on top, and we'll end up with something that looks a bit like this in the end. Now, of course, I want that to be equal to 0 for a minimum point. I want that to be equal to 0. Now, that seems like quite a hard equation to solve, because of the mix of exponentials and regular functions. So, okay, is there another way that I can assess this, I guess? And also, doing the second derivative seems quite annoying as well. What I decided to do, and this sketch has nothing to do with the graph that I'm just looking at, but it just demonstrates what I'm going to do. If I can just substitute in x equals 1 to the and show that the gradient is negative, and then substitute in x equals a half and show that the gradient, is negative, is positive there and negative there, then I think that's enough to argue that there's a minimum point between them. I think what I should also do is substitute 1.5 into here, possibly, to show which one is, to show that they're both. Do I need to do that? That will at least avoid me checking this, because if I've got a positive gradient here and a negative gradient there, then there's definitely a minimum point in between. I should also argue at this point that there's no discontinuities in the graph between a half and 1. There is a discontinuity here, maybe. Actually, no, there isn't. Not in this graph. there isn't. It doesn't exist for x is bigger than 4/3, but aside from that, it's all continuous. So, okay, if I can show it's negative gradient here and positive gradient here, there must be a turning point, a minimum point somewhere in between. I don't think I need to assess anything about a half and one itself. I think I'm good just to put them into this gradient. Yeah, I think that's just about enough. So I'll put in 1 into here, and I'll put in a half into here, and I'll show that 1 is positive and 1 is negative. So okay, if we put in a half, we can put in a half into there not too difficultly. It becomes this, which is this. And now I want to show that's negative, right? I want to show that's negative. So I need to pick worst case scenario here. So let's choose the biggest possible value of e. I know it's less than 67/24, but I'm going to put that in anyway. And if it's negative for this, it must be negative for the real value of e. So, okay, we do some maths. Some cancelling happens here, which is nice. It's a bit annoying, this, but okay. So the bigger, even if we use an e value that's slightly bigger than what we know it to be, this gradient is negative at x equals a half. So that's fantastic. And now we'll do the same thing for x equals 1. So put that all in, we get this, we get this. We want to show that's positive. So let's choose the lowest possible value of e, because if it's positive for that, it's definitely positive for real e. Put that in, do some maths, cancel some stuff down maybe, and we get that's positive as well. So it definitely looks like this V shape, and so therefore has a minimum in between. And I think that's basically all that I needed to say. Now it's asking me to sketch the entire thing. So okay, let's get out some axes here. It doesn't exist beyond 4/3, which is maybe the first thing to say. Next thing to say is, and I'm going to do this similar to how I did the question before this one, about just combining two graphs together. So I know that this graph, it just looks like this, right? It's just an exponential graph, goes through at 3 because when x is 0, this is 3. So that's fine. Now this graph is a log graph, a little bit more complicated to draw. But if you think about the basic log graph, which PowerPoint draws terribly, but okay, it looks a bit like this, right? It's such a terrible picture. Anyway, if you put a minus x in here, that just flips it in the y-axis, right? So it looks a bit like this. And then if you add 4/3 to the x value, that shifts right 4/3. So it ends up looking like this with the asymptote there at 4/3 rather than at 0 where it previously was. So okay, it looks like this, and then this one looks like this, and all we have to do is add them together. So take any for any x coordinate, just add up the two y coordinates you get. So let's think this through. For massively negative values of x, it's going to be 0 plus a very big number, which is a very big number. So it's going to be all the way up here. For 0, it's going to be 3 plus some positive number, so that's going to be up here somewhere. Doesn't really matter where, does it? And now for any number close to the asymptote, it's a massive negative number plus some not massive positive number. That's a massive negative number, so it's all the way down there. So it's going to do this kind of thing, except we already showed that between a half and 1, this has a minimum point. So it definitely has a minimum there. So it must go down here, have a minimum, go back up again, and then it must have another maximum somewhere between 1 and 4/3. It must have a maximum, and it goes through like this, and that'll be our terrible PowerPoint sketch.